Let us discuss the distribution of the sample mean of a normal variable. A. When the population variance is known. B. When the population variance is unknown. The population variance is known when the population standard deviation is known. Thus, we can convert or transform the normal variable x to the standard normal score. If the population variance is known and the sample size is large, that is, n is greater than or equal to 30, then we use the formula z is equal to x bar minus mu divided by sigma over the square root of n, where x bar is the sample mean, mu is the population mean, sigma is the population standard deviation, and n is the sample size. Let us consider this given problem. Suppose the scores of grade 11 students in statistics are normally distributed with mean of 30 and standard deviation of 10. A sample size of 35 is taken from the population. What is the probability that a single sample will have a mean score of greater than 33? So we're going to use the formula z is equal to x bar minus mu divided by sigma over the square root of n. Substituting the values, we have 33 minus 30 divided by 10 over the square root of 35. So we have 3 divided by 10 over 5.92. So 5.92 is the square root of 35. Then 10 divided by 5.92 is 1.69. Then 3 divided by 1.69 is equal to 1.78. And now, we're going to locate the corresponding area of the z-score, which is 1.78 in the z-table. And the corresponding area in the z-table is 0.96246. And we subtract the area, which is 0.96246 from 1, because we are applying here case number 2, which is greater than z. So 1 minus 0.96246 is equal to 0.03754, which is equal to 3.75%. Therefore, there is a 3.75% that a single sample will have a mean score that is greater than 33. Letter B, when the population variance is unknown. So the population variance is unknown when the population standard deviation is not given. Thus, we cannot transform the normal variable x to the standard normal score. However, we can estimate the population standard deviation using the sample standard deviation and transform the given variable to a variable with a similar distribution, which is the t-distribution. The t-distribution is indexed by the degrees of freedom. The degrees of freedom refers to the maximum number of logically independent values which have the freedom to vary, denoted by df is equal to n minus 1. So as the degrees of freedom increase, the t-distribution approaches the standard normal distribution. In the t-table, you can see the degrees of freedom on the first column, where the degrees of freedom is equal to n minus 1, meaning the degrees of freedom is equal to the given sample size minus 1. On the upper row, you can also see one tail, two tails, with their corresponding decimals in its column. So when do we use one-tailed and two-tailed? We use one-tailed when you are interested on one direction. And the term used is less than the variable x or more than the variable x. And we use two-tailed when you are interested on both directions. And the term being used is less than and or more than x. Here are the models of a one-tailed and a two-tailed. For a one-tailed, you can see a model which implies that we only get the area of less than the given variable x, and a model which implies that we only get the area of more than the given variable x. For two-tailed, you can see a model which implies that we get the area of both less than and more than the variable x. Let us consider this given problem. Suppose the scores of grade 11 students in statistics are normally distributed with mean of 30. A sample size of 20 is taken from the population and the scores taken show a standard deviation of 8. What is the probability that a single sample will have a mean score that is greater than 33? So here we're going to use the formula T is equal to x bar minus mu divided by S over the square root of n. So substituting the values, we have 33 minus 30 divided by 8 over the square root of 20. And we have 3 divided by 8 over 4.47. So 4.47 is the square root of 20. Then 8 divided by 4.47 is equal to 1.79. And 3 divided by 1.79 is equal to 1.68. First, let us find the degrees of freedom, which is equal to n minus 1. So our sample size is 20 minus 1 is equal to 19. Therefore, the degrees of freedom is equal to 19. And our computed t-value is 1.68. Now, locate the degrees of freedom, which is 19, on the t-table. Then find the values in this row where the computed t-value is in between. And these are 1.729 and 1.328. So, the computed t-value, which is 1.68, is in between 1.729 and 1.328. So here, we're going to use a one-tailed test because we are looking for the probability of a sample mean which is greater than 33. So for the column where 1.729 is located, we have 0.05. And for the column where 1.328 is located, we have 0.10. So the probability of t-value which is greater than 1.729 is equal to 0.05 or 5%. And the probability of t-value which is greater than 1.328 is equal to 0.10 or 10%. Therefore, the probability that a single sample mean will be greater than 33 is between 5% to 10%.